Trig Ratios Part 1 by Jeff Simpson, MasteryLearningSystems.com. Trig is short for trigonometry. Trigonometry comes from two Greek words meaning triangle measure. Measuring right triangles is a big part of trigonometry. Triangles themselves can be measured, and triangles can be used to measure other things. For example, in astronomy, in surveying, in measuring distances, in navigation, and so on. Every right triangle has three sides that can be measured. And three angles that are measured. The side measurements can be compared by using ratios. For example, 3 to 4, 4 to 3, 3 to 5, and so on. But maybe that doesn't make much sense to you, so here's a quick review of ratios. A ratio compares two numbers. We can use a ratio to compare the length of side A of the triangle to the length of side B. Side A is 3, side B is 4. Side A compared to side B, the ratio is 3 to 4. Side B, on the other hand, compared to side A, the ratio is 4 to 3. Here are all 6 ratios for this triangle. Comparing A and B, that's 3 and 4, the ratio of A to B is 3 to 4. But the ratio of B to A is 4 to 3. Let's look at another ratio. Now we're going to compare A and C. 3 and 5. The ratio of A to C is 3 to 5. But the other way around, the ratio of C to A is 5 to 3. And we can also compare B and C. That's 4 and 5. The ratio can be 5 to 4 or 4 to 5. Each of these 6 ratios has a special name. These will be presented later in this video series. So we can have the A and B ratio, the ratios involving A and C, and the two ratios involving B and C. A ratio compares two numbers. For example, the ratio here of head to body is 3 to 4. A proportion compares two ratios that are equal. Now we've enlarged the snowman, and now the head is 6 and the body is 8. Let's look at the 6 to 8 ratio. If you divide both numbers by 2, the ratio reduces to a 3 to 4 ratio, just like the smaller one that we started with. So we can say a 6 to 8 ratio is equal to a 3 to 4 ratio. Notice when the shape is enlarged, the measurements get bigger, but the ratio stays the same. Those ratios are equal. When the whole shape gets bigger, all the parts get bigger, but stay in the same proportion. Uh-oh, look at the nose. One part does not suddenly grow more than all the other parts grew. That would be wrong, out of proportion. You can see this same idea in action with a square. If you change the size of a square, its shape does not change. Its angles do not change. Its side ratios do not change. For example, the sides here are 1 and 1, and the big square, the sides measure 3 and 3. On the left, the ratio is 1 to 1. On the right, the side-to-side ratio is 3 to 3, but that simplifies or reduces to 1 to 1 ratio. The measurements get bigger, but the ratio stays the same. This is also true with half of a square. Here's a square. Use the diagonal, cut it in half, and we have a right triangle. If you change the size of the triangle, its shape does not change. Its angles do not change, and its side ratios do not change. Here, for example, the sides measure 1 and 1, or this one, 3 and 3. On the left, the side-to-side ratio is 1 to 1. On the right, the side-to-side ratio is 3 to 3, but that reduces to the same ratio, 1 to 1. The measurements get bigger, but the ratio stays the same. The same is true with an equilateral triangle. If you change its size, its shape does not change. Its angles do not change. Its side ratios do not change. 1 to 1, 1 to 1. The measurements get bigger, but the ratio stays the same. This is also true with half of an equilateral triangle. And we see the first one has a ratio of 2 to 2, comparing the two sides. Now let's cut that triangle in half, and the ratio of side to side is 2 to 1. Now, if you change its size, ratio is 4 to 2, its shape does not change. Getting bigger. Its angles do not change. And its side ratios do not change. On the left, you see a ratio of 2 to 1. And on the right, you see a ratio of 8 to 4, but that reduces to 2 to 1. It's equal ratio. The measurements get bigger again, but the ratio stays the same. If you double the size of the triangle, all the measurements double. Side A starts off as 3, and it doubles, becomes 6. Side B, smaller, is 4, but it doubles, it becomes 8. Side C goes from 5 up to 10. If you double the size of the triangle, all the ratios stay the same when they're reduced or simplified. For example, the A to B ratio is 6 to 8, but that equals 3 to 4. The A to C ratio is 6 to 10, but that equals 3 to 5. The B to C ratio is 8 to 10, but that reduces to 4 to 5. Now, if you double the size of the triangle, all the angles stay the same. This is an important idea in trigonometry. You can change the size of a right triangle, but its shape stays the same. Its angles stay the same, and its side ratios stay the same. Triangles with exactly the same shape, but a different size, are called similar triangles. Similar is actually a technical term. It means exactly the same shape, but a different size. Any ratio, such as this 5 to 4 ratio, can be reduced, watch this, so that there is a 1 on the bottom in the denominator's place. So now we see a small reduced size picture, and the ratio is 1 and 25/100 to 1. These ratios are the same. They're equal. And any ratio, such as this 5 to 4 ratio, can be reduced so that there is a 1 on the top. You can do it either way. Now the ratio is 1 to 8/10. These ratios are equal. Trig ratios are often reduced, so there is a 1 on the bottom. That means the bottom of the fraction, the denominator's place. Here we see a 3 to 5 ratio being reduced to 0.6 compared to 1. Or a 4 to 5 ratio being reduced so that it's 8/10 compared to 1. When there is a 1 on the bottom of a ratio, math people leave out the 1 because any number divided by 1 does not change. So the ratio of A to C, normally you'd say is 6/10 to 1 or 0.6 to 1. But the way it's done in trigonometry is the ratio of A to C is 6/10. The ratio of B to C is 8/10. When the 1 is left out on the bottom of a ratio, the ratio of A to B being 75/100ths, it doesn't look like a ratio anymore. Or the ratio of A to C is 6/10. Or the ratio of B to C is 8/10. If you want it to look like a ratio, which is always a comparison of two amounts, well, just write a 1 under the abbreviated ratio, and you can see it's such and such compared to 1. At first, it may seem annoying to have a ratio that looks like a decimal and does not even look like a ratio, like this one. The ratio of A to B is 0.75. But it turns out that having a ratio in the form of a decimal makes some math work much easier to do. Here's an example. Let's say you have a right triangle whose base is 20 inches long, but you don't know the height. We'll call the missing measurement of the height x. You've been told that the A to B ratio is 75/100ths. We can see that the A to B ratio is the same as the x to 20 ratio, so we can write that as an equation. A is to B as x is to 20. And we know that ratio is 0.75, 75/100ths, so we can change the equation, and now it looks like 75/100ths equals x over 20. Now, do the math. Multiply both sides of the equation times 20. Cancel the 20s on the right side of the equation. Now the equation looks like 20 times 75/100ths equals x. Now solve for x by multiplying 20 times 75/100ths. You may use a calculator and find that x is 15. 20 times 75/100ths equals x. 20 is the measurement of the base. 75/100ths is the ratio. X is the height. We multiply the base times the ratio to find the missing height. Very convenient. Here we see the math. 20 is the base times the ratio gives us the height. Every square in the world has predictable angles and side-to-side ratios. Whether the square is big or small, the angles and the ratios are always the same. And every square contains two right triangles. Actually, every square contains many right triangles. Every equilateral triangle in the world also has predictable angles and side-to-side ratios. Whether the equilateral triangle is big or small, the angles and the ratios are the same. And every equilateral triangle contains two right triangles. What about circles? Do they contain any right triangles? Does every circle in the world have predictable angles and side-to-side ratios? Well, there aren't any straight lines, so how can you have angles and ratios? You can use three circles to create triangles. But how can you make right triangles in a circle? Just as we did with the square, we can cut the circle into smaller parts and make right triangles that way. Every circle contains many right triangles. Here is a simpler way to make right triangles with a circle. Continue with the next videos in this series to learn more about using circles to create right triangles. And they will have angles and ratios that can be named and measured. Thanks for watching my video. Please share these ideas with people who can benefit from them.